Alright guys, so I did see most of you guys did your Google form online homework. How long did that take?
Not long.
5 to 10 minutes maybe?
I took like an hour break.
The time of the tornado drill. Yes, okay, so I mean there's a timestamp. I can tell when you guys do things, and I can tell when you're up at like 2 a.m. Please, good Lord, get some sleep, people. Like, don't sacrifice your sleep. Okay? It'll come. Like, the grades will come, but you know, your brain doesn't work well if it doesn't sleep. You know that, right? And then it just is a snowball effect. So if for some reason, like there's games and there's this event with family that you can't get out of because you know it's family, and you're just like, Inlo, I totally did not have enough time for the homework. I'm not gonna be mad. I don't get mad. We don't cry over spilled milk. That's just my talking. I don't cry over spilled milk. I want to make sure that you're getting the support you need to get where you need to be at the finish line. You know, we gotta stop and take a breath sometimes on a 5K, 10K, marathon, whatever. But if we can make it to the finish line, I'm a happy camper. Does that make sense? Okay. So I'm gonna ask for a couple responses on these. You guys got a good idea from your notes on this, but we're gonna get an even better idea what this looks like in the lab today. Okay, so I'm hoping to spend no more than 10 minutes up here. And our lab is 1, learning how to light a Bunsen burner, and 2, a chemical and physical changes lab. So you'll reinforce some of these findings. All right, so first off, distinguishing a chemical from a physical change. I need this as incredibly generic as you can make it. Evan, go.
Chemical changes are irreversible while physical changes are reversible.
So generally we say these are irreversible. That's not irreversible. And then chemical. There we go. So generally say that, though that's still a generic enough statement that there are some exceptions, but we'll try to stick with that for now. And let me get another one. Olivia, give me something else that's a distinguishing factor between chemical and physical.
Chemical kind of changes everything, and physical just kind of changes everything.
Okay, so physical will be more about its appearance, and chemical will be, I'm going to say everything, which could include things like what? Okay, composition is the big word of the day, okay? It's composition, that's the big thing, but also we could say that's its state of matter. Not its state of matter, but it could change to a totally different state of matter because it's a totally different thing at this point. Solid changing to liquid or liquid changing to solid can sometimes mean it's a totally new substance. That's a decent enough distinguishing mark there. Okay. Now sometimes there's those in the middle that it's kind of difficult to tell what's going on. So Kelsey, what would be a good way to distinguish? Or sorry, why would they not always be straightforward?
Some physical changes are like changing the state of matter,
Okay, so sometimes the change of phase or state of matter can be a little weird because you have to think about, like, did I keep the composition and just melt it? Did I keep the composition and just evaporate it? Did I keep the composition and just solidify it? So you really got to know what's going on to understand what the state of matter is occurring. Or did I make something totally new that it looks like a solid now? Because sometimes the way it looks is you put 2 liquids together, and you guys should know the word for this now, okay? You put 2 liquids together, boom, a solid form. What is that called? Precipitate. And sometimes you have a clear liquid, and boom, your solid is yellow. Well, I see the precipitate forming because it's solid, but I also see another change. Color change. So is color change always chemical? No, that's the weird one, because that's the one where you have this idea, okay, so color change that's expected, it's going to be most of the time what? Physical or chemical? Physical. And so the color change that's expected, we'll most of the time call it physical. An example of that would be like food dye in water. Water's clear, food dye is blue. I put food dye in water, what happens? It turns blue, and you're like, oh man, it's a color change. But it's an expected one where you're just making a mixture of 2 things, one of which has a color. So a mixture, though, never has bonded chemically together. I could totally separate food coloring from water via distillation or something, okay? So that's a mixture that we made. However, you also have the color changes that are unexpected. Oops, unexpected. So if it's unexpected, generally, we'll call it what, Anthony? Work with me. I know, but work with me for a moment. Unexpected color change will generally be labeled as chemical or physical change. I'm going to go with chemical just for the moment, and occasionally it could be physical, but it's usually we can see a color coming in to mix with something else. So generally this one would be a chemical change, and the example I just said earlier was like a liquid plus a liquid, making it solid. You guys call the solid a what? A precipitate, and occasionally some precipitates have colors, and you wouldn't expect two clear liquids to coming together to make like a yellow precipitate. So hopefully you guys will see some of that in the lab today. I will go over the highly missed questions after I finish scoring them, and I will email you your grades back. If you haven't done it, you should probably do it for a late grade. Okay, so questions on chemical and physical for the moment. Try to make eye contact. Okay, I'm working on mind reading. I'm not there yet. So, quick one more time review of energy in the relationship to dimensional analysis, which is just a conversion process. So I want you guys to look, actually we'll do this one first. I know you guys know how to do this. We've talked about this before, but we're going to go and solve this problem. 25 degrees Celsius. What do you do to make it Kelvin? Everybody. Okay, so Celsius plus 273 is what here? 298 Kelvin. So that will be our answer in the SI unit that is preferred for the system of international measurement. Okay, and then going from Kelvin to Celsius, Evan, pick up there. Right, so we're going to take 0 Kelvin, does not say okay, 0 Kelvin minus 273, and that's going to give us our Celsius, which would be what? Negative 273 degrees Celsius. And that's our absolute zero, theoretical minimum temperature that we can really get anything to. What's the theory at absolute zero? Anybody? The molecules stop moving, right? So there's no more movement at all. So what's cool about that is that means like every tiny particle atom in your body right now is moving. It's vibrating. But it's moving and vibrating, but the molecules that are next to each other have a bond or have a liking for each other. They're attracted to each other. If every molecule in your body didn't like each other, I could walk right through you. But your molecules like each other enough, and my molecules like each other enough, will repel, which means I bump into you and we repel. But if your molecules didn't like each other as well as, and my molecules don't like each other, meaning like attractions there, I could walk straight through everybody. And then like matter would fall right through our hands. Okay.
Would you like to fall to the ground?
Yeah, I don't know where we end up, someplace. Our molecules are so engineered to be attracted to each other, that's not a thing you can try. But in theory, if we reverse the poles on everybody's molecules, they probably just rearrange in a different order. Like reversing the poles like on a magnet, our molecules would just rearrange and we'd look different, but they would still end up in an arranged format. Yeah.
So would you be dead if they froze you to that?
So they've never gotten to that point, right? So they don't exactly know. This is why it's a theory. They don't exactly know, but they assume that all motion will stop because motion is a measurement of kinetic energy. And so temperature is a measurement of kinetic energy as well. I wouldn't say you'd be dead because potentially things could come back, right? What do they call that? Not crystallography. Correct. Cryogenics.
Oh, yeah.
Then my stutter come out there. Okay. So cryogenics. But yeah, it's a thing. What's up?
Yeah, so why did they get like negative 273? Like, did they just go to 0 Kelvin, or did they like take the negative 272?
So it's actually negative 273.15. That's the more specific constant. We've made it to negative 273, but we've never made it to negative 273.15. And so we've gotten to the point where almost all matter stops moving, but not quite. We're doing this, but those people that do the hard science. Okay. All right, so speaking of energy in general, we'll usually use joules as our SI unit for energy. So joules, and if you've ever, I think at IKEA, they have like food section. I think they measure their energy in joules, or it's calorie. So check that out next time you're there. A lot of European nations will utilize joules or kilocalories versus big C calories. So like, Austin, what did you have for lunch?
I had a sandwich, peanut butter and jelly.
Peanut butter and jelly. So peanut butter and jelly is probably like, 400-ish calories. Okay, so we're gonna do 400 big C calories for the PB&J. Okay, two pieces of bread, like 150. Peanut butter is about 200. Jelly 50 to 100. So that's what you got there. So we're gonna take your lunch and we're gonna convert it to joules. So what actually happens happens in America is our big C calorie here truly means 1,000 little calories, little c calories. They give us the big C calorie because they don't trust that we know what a K means. I know you guys know what a K means, but the general person out in the world does not. So K means kilo, right?
Yes.
So 1 kilocal contains how many calories? 1,000 calories. Okay? So technically, in all reality, your 400 calorie sandwich was 400,000 calories. Okay? Which most people will be like, oh my gosh, I have to starve myself. I can't eat this. Right? You can't do it because that's 400,000 calories. But our body utilizes little C calories. Our body doesn't utilize the big C calories, the big kilocalories, because that's actually a lot of calories together. What's up?
So they just assume that everyone
They assume that the general person would not understand the technicality of a difference in measurement. That is my goal in life, to teach you about calories. However, I can't reach every person in the USA. So, but we're going to take this and go to joules, okay? So 1 big C calorie, instead of writing as a big C, I'd rather use the K because I know you guys are smart cookies and you can handle it. So 400 kilocalories, and I sometimes just do multiplication and then a division sign. It's the same thing as the fence that we've been doing. So 1 kilocal contains 1,000 calories, or little c calories, and then from there, I want you guys to convert from calories to joules using this conversion. So, what goes on bottom? 1 calorie, and what goes on top? Okay, can you guys do that math in your head? 400,000 times 4, 16, so 1.6 million and some change. I think that's right. Can we verify? I'm the only one with the calculator out. I might totally be wrong mathematically. Times 1.672 times 10 to the 6 joules. So that is 1.6 million 1,672,000 joules. Man, how do you feel? You feel full now? That's not getting enough energy to fuel your brain. You guys need approximately 200 or 2.5 million calories, little C calories a day. Not big C calories. All right, who learned something about food? Yeah. Any last minute questions about just conversions? All right, so I did give your PS3Bs back. I tried to annotate some things that were necessary to give you some feedback. Some of you guys turned in not all the problem set. If I said resubmit or do some more practice problems, just for your own purposes. If I did say resubmit to me and I will regrade something. There are only very few people who I said to do that. All right, we're going to skip this for now because I'm not ready to do that. Pull a piece of paper. We're going to do our lab. So this is a lab. I'm going to explain why you pull up the paper. This is a lab where actually, look at some of your first day packets. I think I printed the data sheet for this. That one next to the sheet packets. Just want to make sure I actually printed that. Alright, so it was like a piece of paper with the actual one. So I gave you guys this data sheet. It's on the same paper as the reading guides. So I gave you the data sheet so that, you know, my little perfectionists out there draw some data tables. You take 10 minutes to draw a data table. I got you. Okay? Because you guys spend way too long drawing data tables. So I gave that to you just so you could utilize that for ease of taking down the observations you're making. But you can use the back of it if you want to do the purpose and any other questions that need to be answered, because that may not be enough space for you, but I just want to provide that for you up front. So first thing we're going to do is learn how to light a Bunsen burner, and I need you to pay like incredible attention to that, because I will not reteach how to light a Bunsen burner every single time you use a Bunsen burner. There's a specific set of steps, and looking up here for me, okay? There are 4 questions on the Bunsen burner lab. I'll probably spend maybe 10 minutes there, and then I'll say, if you're not done, we're moving on. You can go back and answer those questions later. The physical and chemical changes lab does mean you need to wear your safety glasses at all times. Wearing your safety glasses on your forehead does not help you, okay? So keep them on. And then make sure you're using clean things. Make sure your graduate cylinders are clean. Make sure your pipettes are clean. Make sure your scupula, which looks like a scoop or a long spatula, Make sure that's clean before you start sticking it into my chemicals, because those are all stock chemicals, meaning that from the stock room, they're pure. We will be lighting matches for some of this. So my rule for lighting matches, you light it, you don't blow it out, because you don't blow it out because it makes smoke in the room, and instead we'll just dunk it into a beaker of water. That's why I said the very first thing we'll do is just get a 100 ml. I took attendance. That's it.
Okay.
Reading for a second.
So, sorry, back here. There are 5 main steps. Look on your data table. Do you see it says 1A, 2A, I'm sorry, 1A, 1B, 2A, 2B, blah, blah, blah?
Yes.
Every single step that you are taking, that reaction that you're completing in the lab, there'll be at least 1 chemical and 1 physical change you're looking for. So, make up your mind now. Do you want all your A's to be the chemicals, or all your B's to be the chemical change? So, for every single step, you'll see 1 what? Chemical change and 1 physical change. That's why there are 2 spots for each of the steps from the lab. So, speaking of those steps, one of those steps I provided you with, in step 3, I provided you with silver nitrate, AgNO3, silver nitrate. It will turn your hands black if you get on your hands. Cool. It will like make a stain. It kills your cells. Not cool. Okay, so that cool. That is going to be something you don't want to get on your skin. You don't really want to get anything on your skin, but specifically that one. In the lab, I think it calls for 10 drops in the lab. 5 drops will do, and I only say that because it's made of silver, right? So it's like $100 a bottle. So I just try to be conservative with that. Step 4, alert, step 4. I'd probably put this on step 4, A or B, whichever one you choose. I have cut the magnesium ribbon for you. What did I do for you? Okay, did I do a physical or a chemical change? Okay, so note to self, I've done that for you, because in step 4, you may not find another physical. So I'm telling you that now, so you can note that on your step 4 answer sheet that you have. You picking up what I'm putting down? Like colas.
Like 4B?
Sure, 4B. 4, whichever one you're putting it under, 4A or 4B, but it's in step 4. I have cut magnesium ribbon for you. Ribbon, it's actually like a piece of ribbon, it's metal, and I took this one big piece and I cut it into little bitty pieces for you. So I did a physical change, and what's the justification for that? Why are you calling it a physical change? So composition didn't change. What did I change? It's the shape or the size. Those are some ways that you would describe or explain your evidence. The last bit,
The last bit under that step 3
is after you get your magnesium ribbon, I'll actually hand that to you because it's a little bitty piece and you might lose it. I'll hand that to you personally. You'll put some HCl, so this is concentrated 6 molar acid. That means it's super concentrated. It's not going to burn your skin immediately, but come forward period, you'll be like, man, my skin is a little itchy. Okay, so don't put that in your hand either. So whenever you get to that piece, it's going to step 4. You're going to add your 3 pieces of magnesium and a couple of drops of HCl to a test tube, and a reaction is going to start happening. If it starts producing a lot of gas, and you're like, oh, then go to the fume hood and put it under the fume hood and let it finish. It shouldn't be that much. Just don't like hover over it and walk it. Let it be. Now, we're going to finish all step 1, 2, and 3, 4 kind of together to get us to the point where we're good to go. With step 5, which is actually utilizing the Bunsen burner that we learned how to light before the lab even started. Okay? So step 5, you'll relight the Bunsen burner, and we're going to make a flammable gas. We're going to make hydrogen gas. So, not in step 5. We're going to make a hydrogen gas in step 4. So I want to make sure we're all done with step 4 before we light the Bunsen burner, because then what could happen? Okay. So we don't want any like little flammable gases floating around my room the minute we light the Bunsen burner. So at the very end, you have to keep everything back in your tote. So put everything back where it came from, and wipe down your lab bench. Make sure it's clean. All the chemicals that I tell you can go down the drain can go down the drain with excess water. So we need you to flush water after it for like a minute. So yeah, we waste a little water. The things that are solids, would you want to put them down the drain? Probably not, right? You don't do it at home, hopefully. So solids don't go down the drain. I will set up a filter, which is filter paper in a funnel. I'll set it up for you. You guys can dump your stuff in there. I will probably stop and yell, stop and yell, stop and yell. It's not because I'm mad. It's just because I want to make sure we're all on the same page. Okay? So, same lab groups, lab notebook, chemical and physical changes, and the Bunsen burner lab, which is, they're really close to each other. You may not if you use that. You can write everything on the back.
So you said you tell me about these pictures?
Do not mess with them. Do not mess with my toys. I'm eating, sorry.
Mine said resubmit. You just want me to redo it.
Turn in the pieces that you didn't turn in.
Okay, so I had like 3 problems. And then
Something else.
4.
Yeah, I need you to read. So yours was like, yours like you're helping me across a lot. I don't know why you're doing it. It was a little weird. But talk later. Okay, it's lost.
Okay.
All right, guys, you have your glasses on. You have your lab notebook out. I'm going to show you how lab notebook works, but please don't questions. I'll teach you to try to get enough. All right, I'm still waiting on some to go lab notebook out. So hair is pulled back. Ladies and gentlemen, hair is pulled back. Okay. Roll your sleeves up. I'm not giving you any names today. Okay. So glasses are on. All right. So basically, the gas is on. And how do I know this? Because I can turn this, and the gas comes out of the jet. But I have an emergency thing in the back that I can turn off if I need to. So follow my instructions specifically so we can do this together. I'm sorry, you guys, if you don't mind. I'm going to show you. So, you guys can do that. Everybody hold up the Bunsen burner. One person, of course, not everybody. But I'm going to need you guys to be quiet. Okay? So, holding your Bunsen burner. The latex end is over here. If you're allergic to latex, do not touch that end. This is the place where the gas will be coming out. Okay? So, we're going to go ahead and put this on the gas valve. In the perpendicular position, it is off, right? So we're going to stick this on the gas valve. You have to wait on there. Get the elbow grease in there. It's probably about halfway up. Okay, still halfway on. Right, shut off. Halfway on. Okay, so now, looking back at me. Guys, look at the butt of the Bunsen burner. Hold it up and look at the butt. Oh, I'll give you guys another one. Hey, look underneath that little camera.
Yeah, we only have one of those.
Somebody said out loud, but for me, no.
Wow.
And it's at a meeting, so they didn't do all in my back. Here. All right, sorry. Back to business. Here we go. Guys, we have a butt. Okay, looking at the butt, it's a little like gear-looking silver piece. Righty-tighty. Turn it to the right. Okay, it's always to the right. Don't tighten it, but it's righty-tighty, meaning it's closed all the way. No gas will come through. Take your hand and do a half turn. Half turn. Okay. Half turn on the butt. That's where the gas from this jet is going to come through. We don't need a flamethrower in here. We need a Bunsen. Now we're going to look down the barrel. This is not a good idea, but look down the barrel. Okay? And now we're going to do the same thing. Righty-tighty. Righty-tighty. Turning it to the right. So it's all the way closed. This is called the barrel. The barrel is going to allow a certain amount of oxygen to come in so that we can then allow the gas to become combusted with a spark. So now the barrel is all the way tight. We're going to turn it to the right. I'm sorry, to the left. 4 full turns. But I can't be sure that somebody's not here. Oh, look at that. Half. What? Opening it up. Half. 2. Half. 3. Half. 4 full turns. We're in the lab. back to you, back to you. Okay, there you call me back? Okay, cool, thanks. So everybody now looking at the barrel as a whole, from the base where the gas comes in to the top of the barrel, there's a little hole, a little gap in the spiral screw area. There's a word for that. The threads of the barrel there. Okay? That gap is where oxygen will come in. That is plenty of oxygen. It's like there's a gap right there. It's not very big, but it's a gap. Okay? So, what am I doing? I'm actually talking you through this box right here, where it says, step 1 second. Step 1, close gas intake valve and open 180 degrees. That's a half turn. Step 2, close barrel completely and open 4 complete turns. What step are we on? We basically already done step what? We've done step 2 and we've done step 3, right?
Yeah.
And we've connected to the gas outlet. Now, here's where the striker comes in, okay? So the way that I encourage you to try first is who's a right-handed person? Majority rules. Okay, so I'm going to show you, hold it in your left hand. Whoever's trying first, hold it in your left hand. Okay, so you're holding in your left hand. Let me try. Fine. Oh, it's okay. Guys, I did not say to strike anything yet. You've got to follow instructions or we are sitting back down. This is our first big boy lab. Let's put the big boy pants on. Alright, so you're holding in your left hand and your left thumb is on the side closest to you, the rest of your hand's on the other side. Basically, all you want to do is you just want to use the flint that's inside. There's flint inside. Oh, this one is like destroyed. Let me get another one. There's some that have really good flint and some that have some crappy flint. So there's flint in there, and all the flint needs to do is just strike across the coarse edge there. So your thumb's going to push across, your other thumb's going to help give it pressure, and you're just going to scooch across to get a spark. Okay? So the goal is if you can get it in 3 times. If you can't strike it in 3 times to get a spark, the next person needs to try. Go ahead and try. I'll pass it on more. Alright, I still haven't shown you how to light it yet, guys. I just want to make sure you can spark it. Okay. Okay. 3, 2, 1. Eyes back over here. Okay? So Savannah is going to stand over here with me so everybody behind you can see. So what you're going to do now. Okay, so my lovely assistant here. I'm going to hold the striker over top of her head. Which I spark it this way because you don't have as much pressure with your forearm. That's why you need to have 2 hands on so you can strike. Okay? So what's going to happen now is she's going to turn the valve from the perpendicular to the parallel position, but not all the way back. It's going to turn back off. So it's parallel. And she's going to give me a 3, 2, 1, and I'm going to strike. If I can't get it 3 times, I'm out. Baseball. Okay? Ready? 3, 2, 1, 4. Yeah. 3, 2, 1. Okay, so. Okay. So I got another one. Sometimes you can hear the gas go. It has a hiss. Sometimes it takes a minute to like get in there. And occasionally, if our gas is not prepped, our burner is not correctly prepped, the bottom's open too wide, it means it's going to be like a flamethrower coming out when it comes in. Okay? But what you're noticing here is there's a nice clear blue cone. The inner blue cone is the hottest of everything here. So when I'm burning something, and I want it to be burnt, or I want it to be hotly or warm or heated very, very quickly, or hot or warm, but heated very quickly, it's going to go inside the inner blue cone. Other times I'm going to hold things above it because the heat's coming off the top. Like it's hot up here. So what you'll notice is if I change the oxygen, it gets yellow, it gets kind of wonky, it gets kind of crazy looking over here. We don't want that. That's why I told you exactly how to prep it so that it preps it the perfect way. But some of the questions are going to ask you, what happens if too few or too little or too much oxygen? Go, figure this out. Guys, one thing I failed to mention, stop. Okay. One thing that I failed to mention is that when the gas is not lit in 3 strikes, the gas is still coming out. You're just not good enough to get it lit, right? So you turn the gas off, or you're gonna gas on. One room is open sign started in gas today, and it's just because there's a faulty valve, and I want to deal with that, and I'm not going to deal with you. So I need you guys to make sure to turn it off. Make sure you're in a good position. You're not like, turn it off and let somebody else go. I'm not looking at that. I'm
Oh my God. That was so close. Alright guys, I'm here to fix up the lane. You got 1 more minute to get on my
Alright guys, switching modes, read, sorry, cut on some burners off. Cut on some burners off. Read chemical and physical change intro, and then we're gonna get started, okay? Cut on some burners off. You're going to like, moving on. I'm moving on. Chemical and physical changes. Start reading. I just don't know what time. Don't worry about the question yet. We have time to go back. Read chemical and physical changes loud entirely before we start moving on.
We only need one.
Okay, guys, listen, 5, 4, 3, 2, 1. A lot of you guys have 8 to 12 hands at a table, right? It's a lot of mess that can happen. There's a lot of laughter that can be moved. So I want you to take it a little slow. I want you to make sure everyone's on the same page in step 1. What is step 1? Read this to me. Read it. Let's see what?
All pieces of clay on the table.
Okay, find your play. It's in the little text. There should be a little play on the table and what?
Place the candle, operate in the clay, and light the candle.
Okay, so at this point, this is where you're starting to think chemical change, physical change, chemical change, physical change. In these conversations, you need to be saying, oh, how did I just roll this clay together? Let's talk about what happened and how do I know that chemical or physical change. So you have to go slow enough so that you can make your observations and you can write them down on your paper. You will forget when you get to step 5 what you did in step 1, so you need to take documents of that as you go on your data table, okay? Second thought, one second. I have matchboxes for you guys to strike your matches with, okay? You can have matches, there's plenty of things at your table. Double check the labels as you go so that you're sure you're using the right chemical. Also, this magnesium ribbon I told you about before, I have it here. I'm going to bring you guys a couple of pieces. And then as you guys get in the hang of things, one person in your group can do step 1, one person can start step 2, but I wouldn't start doing anything at the same time because you guys need to talk about your observations. Any questions? Move slow. Yeah. Thank you. My responsibility is right for motivation. Thank you.
So we only need this for water. We only need this
Hey, how are you doing? The what? The wick?